Welcome to The Explainer. Today, we're pulling back the curtain on a subject that, let's be honest, can sound a little intimidating: calculus. But we're going to break it down and show you what it really is, a surprisingly intuitive way to understand a world that's always in motion.
So let's get right into it. The math you're probably used to, like algebra or geometry, mostly deals with things that are static, things that hold still. Well, calculus is the complete opposite. It's the math of things that don't sit still. It's all about change and motion, like figuring out the exact speed of this diver at any single instant in their flight.
And the entire story of calculus really just boils down to solving two huge problems that kept mathematicians scratching their heads for centuries. And if you can wrap your head around these two ideas, you've basically unlocked the heart of calculus.
So let's dive into that first puzzle. Picture a car on a curvy road. How do you figure out its exact speed and direction at one single moment in time? In the language of geometry, we call this the tangent problem. How in the world do you find the slope of a curve at just a single point?
A really good way to picture a tangent line is to think about a speck of dust on a spinning wheel. If that speck suddenly flies off, the path it takes, that straight line, is the tangent. It just kisses the curve at that one point, perfectly capturing the direction of motion in that one instant.
And right there, that's the big problem. I mean, everything we learned in algebra about finding slope, rise over run, it always needs 2 points. But with a tangent line, we've only got 1 point to work with, this point P. So what do we do now?
Well, the solution here is really clever. It starts with an approximation. We can't find the exact slope we want right away, but we can get really close. What we do is we pick another point on the curve, Q. That's nearby. Then we just draw a straight line through both P and Q. That's called a secant line, and finding its slope, that's easy.
Okay, now here comes the magic. Just imagine taking that second point, Q, and sliding it along the curve, getting it closer and closer and closer to our original point P. As you do that, watch what happens to the secant line. It starts to pivot. And this is the big aha moment. As that gap between P and Q gets infinitely small, the slope of our secant line gets closer and closer to one specific number, and that number is the true exact slope of the tangent line. This amazing idea of approaching a value is called a limit, and it's the absolute foundation of what we call differential calculus.
All right, on to our second major puzzle, which is going to seem totally different at first. For thousands of years, we've known how to find the area of a square or a triangle. But what about a shape that has a curved edge? How do you find its area?
Yeah, our standard geometry toolkit is great for shapes with straight sides. But the second you introduce a curve, like the area underneath this graph, all those simple formulas just don't work anymore.
And just like with the tangent problem, the solution begins with a clever approximation. We take this weird, curvy area and we fill it with a shape we actually understand, the good old rectangle. We just slice the area up into a bunch of thin strips and pretend each one is a rectangle.
Now, of course, this first guess is just a rough estimate. You can see all the little bits that are sticking out or being missed. But what if we made the rectangles skinnier and used a lot more of them? As we increase the number of rectangles, our approximation gets better and better, hugging that curve more accurately. And there it is again, that same powerful idea from the tangent problem. The exact area is the limit of the sum of all those little rectangles as we make them infinitely thin. This process gives us the second major branch of calculus, integral calculus.
Okay, so let's recap. We've got two huge problems, and each one created its own branch of calculus. One is all about finding the speed at a single instant, and the other is about finding the total area over a stretch. They seem like they have absolutely nothing to do with each other, or do they?
So on one hand, you have differential calculus. Coming from that tangent problem, it's all about instantaneous change. On the other hand, you have integral calculus, coming from the area problem. It's all about summing up or accumulating change over time.
This was the absolutely brilliant, game-changing insight from people like Isaac Newton and Gottfried Leibniz. They realized that these two totally separate quests, finding slopes and finding areas, were actually deeply connected.
And this is it. This is the fundamental theorem of calculus. What it says is that finding a slope, which is called differentiation, and finding an area, called integration, are just inverse processes. They're like addition and subtraction or multiplication and division. They undo each other. They're two sides of the same coin.
Now, this amazing connection isn't just some neat mathematical trick. It is the very thing that makes calculus one of the most powerful tools ever invented for describing the world around us. It lets us solve an incredible number of real, practical problems.
Think about it. How do you make a roller coaster feel smooth and safe? Well, that's about controlling its rates of change. That's a differential calculus problem. How do you calculate the orbit for a satellite? That's about summing up the tiny effects of gravity over time. That's an integral calculus problem. All of these questions are answered using calculus.
It is truly the language we use to describe our universe in motion. From the massive scale of launching a spacecraft into orbit to the simple fun of launching a model rocket in a field, the same principles are at play. And calculus is what lets us understand, predict, and control them.
And that really brings us to the most important thing to remember. Calculus isn't just a bunch of rules you have to memorize. It's a way of thinking. It's a way to take a really hard problem, break it down into smaller pieces, and as the mathematician George Polius said, experience that awesome feeling, the triumph of discovery for yourself. It's a tool for seeing the hidden rules that govern our changing world.